guy in front of me, which is, what question is that? It's question 7 from 5.1. What you've got here is a function called 1 plus x squared. And this thing here is just an example of what to do. It isn't actually part of the question. It's just to show you how you choose one of these 4 pictures that come later. So what essentially you've got is a function called 1 plus x squared. It's evaluated from -1 to 1. And you're going to do it with 3 strips and then later on with 4. And then you're going to illustrate the diagram with a figure that looks like this. Right? So for n equals 3, you're going to do an upper sum and a lower sum. Okay, so that's the gist of that question. What I'm going to do now is kind of do on paper how I'd go about setting that up. Right. So I'm going to do from x equals 1 and -1, and I'm going to do the 3 strip guy. First thing you need is a sketch, because it's a very visual situation. Now, if I look at 1 plus x squared, I know what it looks like. You can do that in your calculator. Can you imagine this is -1 and this is +1? Now, if you're doing 3 strips, delta x is b take away a over n. That's a, that's b, so what you're going to have is 1 take away -1 over 3. What you're going to get is 2/3. So, oh, oops. Start my little table up. And I'll put the x coordinates here. And I'll put the value of the function at that x coordinate next to it. So we're going to start with -1. If you add 2/3, you end up at -1/3, which is probably about here. If you add another 2/3, you end up +1/3, which is probably about here. And then you finish with 1. So there is the table that we would use to get our 2 estimates. And our estimates are going to be left 3 and right 3, you would expect. But in this story, that's not the case. They want a upper sum and a lower sum. Can you see that this function is increasing and decreasing? So a left 3 or a right 3 wouldn't do the job. So what I'm going to do is I'm going to look at this picture, and we are going to choose 3 rectangles that are going to give me an underestimate, right? A lower estimate. Right, so my first guy could be this side or that side. Would you agree that this side here would give me the rectangle that's smaller than the area? Now, in the middle one, I've got this guy here, right? -3, 3. And I want a rectangle that's an underestimate, and I'm going to take this rectangle that doesn't even use the other side. It's the one that uses 1. That's going to be my second fella. And then the last one can use this side or this side, and I'm going to use that side there, and that's going to be my third rectangle. So if I can find the area of these 3 rectangles and add them up, that is going to be my upper sum, as they call it. And the answer would be written in the box. And then you're going to do a lower sum. And the answer would be written in the box. Now, if you evaluate 1 plus x squared at -1, you get 2. And that's 2. If you plug in a third, you get 1/9. So I guess that's 10/9. And this is also 10/9. So what do I know? I know that this height here is 10/9. I know that this is 10/9. I know the one in the middle is a height of 1. So what would my lower sum look like? Well, that rectangle is 2/3 and its height is 10/9. The middle rectangle is 2/3 and its height is 1. and the end rectangle is 2/3 and its height is 10/9. So this isn't a left 3 or a right 3. This is a 3 rectangles, the 3 smallest rectangles you can get that fit inside the shape. Now, if I finish this guy off, it's 20/27, 2/3, and 20/27. That middle one, if you turn it into 27, so we can combine all the fractions, ends up being 18. So 20/40, 58/27, and that would go in here. Right, suppose you did the same question again. But this time, you want an overestimate. Right, my first strip is here. If I use the left-hand side, I'll get an overestimate. In the middle one, I'd use that. And on the end one, I would use that guy. So for this one, it would be, I don't really got enough room for it, but 2/3 times that height, which is 2. The middle one is 2/3 times the height, which we know is 10/9. And the last one is 2/3 times 2. And can you imagine multiplying all that together and putting your answer in here, which will be so many 27s. So that is not a typical left or right 3. That's a bit messier than that. Now, if I look at the picture underneath and we try and match what I have got, can you see that this picture here represents the darker, slightly darker blue was my underestimate one. And you see these 3 guys here are my overestimate one. And there's my little check mark. And that's the picture I would be picking for that guy. And then you go and you do the same thing for 4 strips. So for each strip, look at what would you use to get the smallest rectangle, right, an underestimate. And then after that, what would you use to get the bigger one? And if you add up all the small rectangles, that will be your lower sum. And if you add up the area of all the bigger rectangles, that would be your upper. So that one is not a typical question, but that's how you would do it. Hopefully that has helped. Now I'd like to show you the rest of, if I can close this off. And just take me a few seconds to get this loaded up. The last question in section 5.1 is quite messy. And so what I have done, I'm now ready to show you, is I've done it for you. So I'm going to show you where it is, and I'll just talk through it. So if we go to here and you see, where the heck is it? Oh, there it is. Help with homework 5.1. If you click on that and you see this guy up here, solution to question 16, that's the one I'm talking about. And why have I got access denied? Okay, let me leave student view and just do it the normal way. There we go. Okay. So I'll make it a little bit bigger for us to see. They ask you in question 16 to find the exact area under the curve y equals x cubed from 0 to 1. And what you can see here is how you go about doing it. And I'm just putting in the working that I used, but essentially the answer to A is this bit here. And the answer to B is what's the exact area, and it ends up being a quarter. Now, later on, I'm going to put a video online where I talk through this with my other class, just so that you can see the stages that I did. We're doing this for completeness sake, so that we can say, look, we've at least shown you the process. I think by just superficially scanning through this, can you see that that process is very long and heavy duty algebra? It's not the way that we actually do find the exact area under a curve. It's the kind of analogy would be, in Calc 1, can you remember those long-winded ways that we found the slope of the tangent line? With all the limit stuff and, you know, x tending to a or h tending to 0 and a whole load of algebra. Remember doing that? But actually, don't you find derivatives in a totally different way than that? Don't you actually just use power rule and, you know, the derivative of e to x is e to the x? That's how you really do it. Well, that's what the analogy is here. The area under this particular curve is a quarter, but I would never solve it by this method. This is like the theoretical way of doing it, but we are going to be able to show you a much quicker way of doing that. So for that reason, I don't want to spend a lot of time worrying you over, oh God, I'll never remember all these steps. But have a look at it and get an insight into the big picture. Of course, you're not going to get a test.
Me too, so I don't know if anyone else can view it, but I can't.
Okay, I'll just go back in and upload it again. I think it might be just because of the way because it was me that uploaded it, it may have given me permission to see it, but not anyone else. So I'll just do it again and fix it. But it will be there by the end of tonight. And that video that I was talking about, where I actually did it with the other class, because some of you like to hear things rather than see things. I'll put that on as well, and I'll put it in the same location as this, so that you can watch a short, about 5-minute video of me doing it, if that would help. So the good news is you are not getting a test question on it, and that's helpful. Also, you're not going to get any test questions on the number crunching stuff. So I'm not going to ask you in a test to find L6 or R6, but you are getting homework questions on it. So you do need to do it for those points. So you are getting tested, at least in that way. So let me return back to the whiteboard and show you the next section.
Do you ever give out practice tests before a test is come up?
Not for these ones, because WebAssign, just the way it's structured, it's not really easy to do that.
Okay.
The best alternate you can have is to realize that your test questions and your midterm questions are going to be on the same. WebAssign's going to create them, so they're going to pretty much look exactly like your homework.
Oh, okay.
You know, so if you go into your homework and, you know, I think there's a feature where you can do extra practice or something. You could do that if you feel you are a little bit, you need more help. Okay, let me show you everybody in town. This is 7-7. 4 questions. Left, right, haven't done it yet, but will. Midpoint, haven't done it yet. Trapezium 4 and Simpson's 4. There are in fact 5 different numerical estimates for the area under a curve. I'm going to show you, hopefully, how you do these. They're not that difficult, really. I don't think they are anyway, but they are tedious. They take forever because there's a lot of button pressing and so on. So let's give you an example. Suppose I had the function f of x equals x squared, and suppose it was going from x equals 0 to x equals 2. And I wanted to do an estimate using 4 strips. And the estimate I'm going to use could be any one of those 5 choices here. We've had lots of practice at left and right, hopefully, so I won't spend any time on them. But you haven't seen trapezium 4, Simpsons 4, and midpoint 4. So let me show you those. No matter what method you use, your first step is going to be to find delta x. In this particular question, it's going to be a half, right? 0.5. That's step one. The second thing that you should do is create your table, because all the numbers that you're going to do, all the calculations, come out of here. And so you start at A, which is 0, and then you go up in 0.5. So 0.5, 1, 1.5, oh, it shows you how well I plan ahead, right? 2.0. Now, if you notice that there's 5 coordinates, for each one of those, you evaluate the function. Now, the one I've done is a nice, easy one, just to make my life and your life a little bit easier. But could you imagine this is really ugly? X squared sine of x cubed. It doesn't really matter what it is. Can't you evaluate it 5 times, right? Just plug it into your calculator and write down the answer. So 0 squared, 0.5 squared, 1 squared, 1.5 squared, and 2 squared. So step 2 will be to create this table. And you will create this table if you wanted to find an L4, an R4, a trapezium 4, or a Simpsons 4. Those 2 steps are identical, nothing different. Now, let's do trapezium 4. It's basically a plug and chug. Here is your formula. It's delta x over 2 times the value of the function at x naught plus 2 times the value of the function at x1, 2 times the value of the function at x2, 2 times the value of the function at x3, and 1 value of the function at x4. And I should have, and I'm now going to do it, remind you who x0, 1, 2, 3, and 4 are, right? So in this question, it's time to plug in the numbers. 0.5 over 2. The value of the function is 0. 2 lots of this guy. 2 lots of this guy. 2 lots of this guy. And you finish with 1 of these. You're basically just following what it tells you. You're comfortable with this magic formula that just, hey, trust me, it works, right? I've given it to you. Delta x divided by 2, the value of the function at the beginning, 2 of all the guys in the middle, and the value of the function at the end. Do you notice that you use all of the numbers? If you were doing right 4, wouldn't you only use the 4 on the right? And if you were doing left 4, wouldn't you only use the 4 on the left? Right. So this is a little bit different, but not a big bit different, right? In fact, maybe it makes more sense. You think if you used all the numbers, it's likely to be more accurate than if you miss one at the beginning or you miss one at the end? Because couldn't that be a really important number that you're missing out? So it is more accurate. So the next stage is you get your calculator. And you essentially try and bevel this so the light's a little bit better. And you just be careful, which for me is very difficult because I'm not a very careful person. 0.5 divided by 2 times a bracket. 0 plus 2 times this number plus 2 times the next plus 2 times the next plus the last number. Close the brackets, enter. And the answer that I have here is 2.1875. And that is an estimate for the area of y equals x squared from 0 to 2. Right, so it's roughly about what, 2.2? Now, I've only given you this fella here for 4 strips. What do you think the formula might look like if you had to do 6 strips? So imagine you had to use the thing to find T6. Well, the delta x over 2 is always going to be delta x over 2 when it's a trapezium. And it's always 1 of the first guy, 2 of the next one, 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 2 of that guy, and you finish with 1 of the last guy. Does that kind of make sense that you can adapt the formula to 5 strips, to 6 strips, good gracious, 8 strips? You comfortable with that? So that is trapezium. Now, excuse me, I'm going to put things on mute. I'm getting some feedback here. If you're wondering where or how does this formula get generated, I'll give you a little background to it. Can you imagine that you take your shape and you break it into the usual strips? If you were doing the left or the right, wouldn't you get rectangles? But can you imagine that instead of that, you draw a line from the top to the bottom and you make a shape that looks like this? So the trapezium rule doesn't add up rectangles, it adds up a whole load of shapes that look like this. Now, can you imagine that that would be more accurate? Because, you know, rectangles leave gaps, don't they, where bits are too much or bits are not enough. But you can see, drawing in a straight line, there's probably going to be a lot less error. This shape's called a trapezium. And if you calculate its area, you basically break it into a little triangle and a little rectangle. You calculate it. This is the formula that gets generated. So if you're wondering where it came from, this is where it came from. Now, in the big scheme of things, left and right are pretty bad estimates. Unless you have tons of strips, a left or a right 4 won't do a great job. A trapezium 4 is better. So for any given number of strips, T10 will always give you a better answer than a left 10 or a right 10. So I guess now that you know that, you probably won't do a left 10 or a right 10, will you? You'll always do a T10, right? Because, you know, for that amount of work, you might as well get the best answer you can get. Now, we haven't done the next guy, but we're about to. And that is Simpson 4. And in Simpson's 4, it's even more accurate than trapezium. When you look at the formula for Simpson's 4, it's quite messy. Delta x over 3, the value of the function, just one of them, 4 of the next guy, only 2 of the next guy, 4 of the next guy, and you finish with 1 of the last guy. So I am now going to use the same question. That's this guy here. And we're now going to get Simpson's 4. So it's going to be delta x over 3, 1 of these, 4 of these, 2 of these, 4 of these, and you finish with 1 of those. Now that would be 0.5 divided by 3. 1 of these guys, 4 of the next guy, 2 of the next answer, 4 of the next answer, and 1 of the last answer. Actually, I could probably do this without my calculator, like most of it. Nothing plus 1 plus 2 plus 9 plus 4. That's pretty good. 13, 14, 15, 16. Half is 16 is 8/3. So it's roughly about 2.667. Now we did T4 a moment ago, and T4 was 2.6667. That wasn't. That's this number. T4 was 2.1875. Do you know what the exact answer is to that? If I did the same process as the question that I've got online, which you'll eventually be able to see, the exact answer is actually 8/3. Simpsons 4 got a perfect result. It's not going to give you a perfect result every time, but if the function is quadratic, or like x squared plus 4x plus 5, it will give a perfect answer. If it's a straight line, it'll give a perfect answer. If it's a cubic, like x cubed plus x, it's a little bit out, but it's typically very close to being the right answer, even with just 4 strips. So that's a very powerful technique, that you can estimate the area under a curve using Simpson's rule. Do you have any questions? Are we good? I couldn't quite hear you. You're kind of quiet, Ryan, so could you?
Does that one have a multiple strip form, or would you only use the 4, 5, or 5 strips?
Oh, you can do it for any number of strips. So let me try and show you what a T6 would look like. It would always be delta x over 3, right? That never changes, no matter how many strips. And the pattern is 1 of this guy, 4 of the next, 2 of the next. And basically just go 1, 4, 2, 4, 2, 4, 2, 4, finish with a 1. So just keep doing 1, 2, 4s, 2, 4s, 2, 4s until you get to the second last one and finish a 1. So this one is actually 1, 2, 3, 4, 5, 6. Oops. 7. So it would be that one. That's what S6 would be. I'll try that again. S6 would be delta x over 3, and the pattern would be 1, 4, 2, 4, 2, 4, and 1. And you just fit in f of x0, f of x1, f of x2, all the way to the last one, f of x6.
How come it alternates like 1, 4, 2, 4? Why does it do that again?
Say that again. Why does it do that?
Yes.
And it's basically, trust me, I'm a mathematician, that's the formula that you use, right? If you want to know where it came from, do you know how the trapezium came by making strips but joining them with a straight line, right? Making those little trapezium shapes. Simpson's rule gets formed by, can you imagine this was one strip and the curve, the function went through it like that? In trapezium, you join there to there with a straight line. In Simpson's rule, you join there to there with a curve. In fact, the curve that you use is a quadratic curve. That's why it's a perfect fit to a quadratic. And the formula that you get when you do this is that ugly one called Simpson's rule. Now, there's a little idiosyncrasy with Simpson's rule. You can only do it for 4 strips, 6, 8, and 10, even numbers of strips. And because the way the formula has to be 1s, 4s, 2s, right? There's a lot of symmetry to it. The only way that works is if you have an even number of strips. But I wouldn't worry about it, because nobody will ever ask you to try and use Simpson's rule on an odd number of strips, because it's a silly question. Right? But I thought I would tell you that. Are you happy with the process of just follow instructions once you've got your table? Do you want to see another one of Simpson's trapezium before I move on to the midpoint one?
Why not?
Why not? Good answer. Right, so I'm going to look right now, though you can't see it. I don't want to bounce in and out. I'm going to look right now and see if I can pick one that's very similar to the homework question. That way, it gives you an idea of a more realistic version. Right, there are only 4 questions, so the guy I'm picking is like question 3. And we're going to be doing the integral from 0 to pi upon 2. I'm going to do the square root, and I'm going to call it 2 plus cosine of x dx. Yeah, that should work. And they want 4 strips. Have we seen this notation before? Isn't this just the area under the curve from 0 to pi upon 4, and this is your function? They could have done the question this way. Find the area under this curve from x equals 0 to pi upon 2 using 4 strips. That is exactly the same as that. The nice thing is, isn't that just a little bit less work? And it's just a more concise way of saying it. Okay, so we're going to do a Simpson's trapezium again with 4 strips. Step 1, find delta x. B take away a over n. Oh, a little bit more awkward. Pi upon 2 take away 0 divided by 4. Can you trust me that that's pi upon 8? Now, step 2 is create the table that you're going to use to get all your answers, all your values from. And it's going to be x0, x1, x2, x3, x4. So yeah, a little bit better planning this time. That's going to be x0. That's going to be the x1, the 2, the 3, and the 4. We're going to start at 0. And delta is pi upon 8. So I'm going to call that pi upon 8. I guess the next one is 2/8 pi. The next one is 3/8 pi. And the last one is 4/8 pi. I guess I could have simplified that. Couldn't have called that a quarter pi and couldn't have called that a half pi. The reason I left them as 8s is just to make it a little bit easier. Can you see? Add an 8th, add another 8th, add another 8th, add your last one. Now, isn't 4/8 pi exactly what it should be? It's a half pi. So I know I've done it right. Now, for each value of x, we then evaluate this ugly guy. And I'm going to try and let the calculator take some of that workload off me. So I'm going to go y equals. I'm going to type in the square root of 2 plus cosine x. I'm going to go to table setup. And table setup is going to start at 0 because my table starts at 0. And it's going to go up pi upon 8. So I'm going to go here and type in pi divided by 8. So that's how I got the table set up, right? And then if I go second table, here are all my answers. At least to 4 decimal places, here they are. 1.7321, 1.7029, 1.6453, 1.5436, and the last one, 1.4142. Okay, let me just pause for a second. Are you comfortable about the general start to all these questions? Even if that had been an L4 or an R4, wouldn't that still be the first two steps? Right, I'd do that with all of them. Now, I then have to decide, based on what they ask, what I'm going to do. Now, they might say find L4, in which case I'll do this. They might say find R4, I'll do that. But let's suppose they said T4, right? Then T4 is going to be delta X over 2, one of these guys, 2 of everybody in the middle, and 1 of the last guy. Okay, I'm going to try this on the calculator. If anybody's good at button pressing, you may want to do it with me, because the chances are I'm going to screw this up. I'll try my best not to. It's pi over 8 being divided by 2. So I'm just going to do that in one go. Pi divided by 16. Then I'm going to go times, bracket, the first guy, plus 2 times the next guy. Plus 2 times the next one. Plus 2 times the next one. And finish with 1 of the last guy. Close the brackets, hit enter. Keep your fingers crossed that I didn't screw up. And 2.5415, at least to 4 decimal places. Now the question might want 6 decimal places, in which case won't you have to make sure that these get filled in with 6 decimal places rather than 4, right? So far so good. That's how you would do a T4. Now, if you want to do an S4, delta X over 3, one of the first guys, then 4, then 2, then 4, and then 1. And this is going to be on my calculator one more time. So it's going to be delta X divided, so that's pi over 16 again. Then go times a bracket, one of the first fellas, times 4 of the next guy, plus 2 times the next guy. I will be so glad when we've finished this section. This drives me crazy. And this time, I'm worried.
Should it be pi over 24 instead of pi over 16?
Yes, it should be. Now, second entry, go back here and do 24. That way I don't have to retype everything. And I'm not so worried anymore. Which rounds off to 2.1420 to 4 decimal places. Did I do the top one over 24 or not? Can you remember? Right. Can you imagine I did do that? Because I'm not going to go back and retype that again. And I did keep my word, didn't I screw up? So you will be extra careful so you don't have to go and redo some of them. Are we a little bit more comfortable now about if someone gives you a function and tells you how many strips and asks you to do a T4, an S4, or maybe a T6, S6, whatever it is they want, that you would create the table and then use 1, 2 of everybody, 1, or a little bit more complicated for Simpson, the 1-4-2 pattern. It's really just laborious. It's right, hit buttons and be careful.
What is the dx that's tacked on to the end of the square root up top?
It's almost equivalent to the delta x, which would be the width of the rectangle. And the
Okay.
delta now becomes a d. It's a notational thing, but it does get used later on. If you remember dy by dx in Calc 1, remember that notation?
Yeah.
It's exactly the same reason that dy by dx is called dy by dx. It basically means the distance in the x direction, right? It's called the differential, and that's why it's there.
Okay.
Now, there's only one guy left. The only guy I haven't shown you how to do is a midpoint. So I'll pick a different question to do a midpoint with. Let's suppose I do the question using this notation, so it's a little bit less writing for me. And I'll do it from 1 to 5. And the function I'm going to do is a pretty easy one, so I don't have too many buttons to press, is x cubed. And we're being asked to do this particular one, right? And we're being asked to do it with five strips. I just want to pick something a little bit awkward so you don't get perfect numbers. Right. Now, step 1, find delta x. So I'm glad that's not anything different. .8. Now, normally what you would do in step 2 is you would create your table. Now, you wouldn't do what I'm about to do, but I'm doing it for kind of completeness sake. You would start at 1 and you would go up in 1.8s. And you'd get that, right? But isn't that the table that you would use for left, right, trapezium, or Simpson? It's not the table that you use for midpoint, because midpoint isn't these x's. Okay, imagine that guy is 1 and that guy is 1.8. So that's like where my first strip would be. The midpoint gets its name because the x coordinate that you use isn't either that or that. It's the guy in the middle, the midpoint. Now, if this guy is 1 and this guy is 1.9, wouldn't the middle be halfway, be 2.8? Wouldn't the middle be 1.4? Are you happy where I got the 1.4 from? So what we really do in step 2 is we create a table, but we create a table where the x coordinates are the midpoints. So the first midpoint is 1.4. Now, the next guy would be here at 2.6. So, oops. Can you imagine that the midpoint is here, right? And between there and there, halfway is equal to 2.2. And we call this guy x1 bar. We call this guy x2 bar. And there are going to be 5 of them altogether. x3 bar, x4 bar, and finally x5 bar. What do you think the next 3 numbers are going to be without me drawing all this picture and adding and halving and doing all sorts of stuff? just looking at these two, you should be able to have a good guess at what the next one is.
Three.
3.
Yeah. And what's the next one?
3.8.
And the last one then?
4.6.
Right. Have you noticed that from one x value to the next, don't you still go up by delta x, which in this case is 0.8? So when you're filling this table in, well, you only work at figuring out who the first guy is, right? Figure out who that guy is. Because once you know him, can't you figure out the rest by just adding 0.8s all the time? Now, again, I want to cut my workload down and reduce my chances of screwing up. Since the function I've picked is x cubed, I'm going to let the calculator do that. And I'm going to plug in x cubed. I'm going to go to table setup. It's going to start at 1 this time. And it's going to go up in 0.8. And I've just screwed up and I've caught myself in time. Does this table start at 1?
1.4.
Exactly. But I caught myself, right? Now, starting at 1.4 and going up in 0.8s will be this table. So when I go second table, there's all my guys waiting for me. At 1.4, it's 2.744. The next guy is 10.648. The next guy is 27. The next guy is 54.872. And the last guy is 97.336. But this is only good to, 3 decimal places. So if you wanted a more accurate answer, won't you just basically have to do a whole load of x cubes on your own? So you would go 3.8 cubed. Let's just show you what that particular one would look like. If I needed more, because they want 6 decimal places, 3.8 cubed. Oh, okay. It's the same answer. Can you imagine it was the sine of x then? The sine of 3.8. Yeah, see, you'd get lots of decimals. So what's the formula for midpoint? Oh, darn it, or nice. Isn't it basically delta x and add them all up? So to get midpoint 5, it's delta x, this guy, this guy, this one, and that one. So what do we have here? Oops, I don't have a delta x anymore. I have a 0.8, and I should really let the calculator take over. So here goes. 0.8 times 2.744, add 10.648, add 27, add 54.872, add 97.336, close the brackets, and the answer is 154.08. I hope. Yeah, it looks reasonable. It could well be correct. Are you comfortable about how to do a midpoint one? Right. Can you be asked to do a midpoint 6, a midpoint 10, a midpoint 4, and you would do delta x. Your table would exist, but won't you have to tweak the table a little bit because it's the midpoint x coordinates that you use. It's not the start or the finish, but the middle, right? And find the first one and then just keep adding delta x's and you've got the rest. Do you want to see another one of these, or are we comfortable with this one example? Your choice, guys. What do you want me to do?
I think I'm okay.
Okay. Anybody disagree with that? Feel free to say yes. Otherwise, I'm moving on. I'm moving on then. You know, if something like this is bugging you, can't you just go back to the video and just look at this piece of the video and pause it and then rewind it and pause it until, yeah, okay, I think I got what he's doing. Because, you know, I do know that it's easy to zoom by some stuff and perhaps not dwell on it as long as I should. And I think we're all guilty of that sometimes. We are ahead of the curve then. There is only 4 questions in 7-7. And well, I think before I move on, let me just show you what the homework questions look like, just in case something comes to your eye and you think, oh, I'm not sure what they want. So here are the 4 questions. Right. I think I could probably make this a bit bigger because I don't know how large your screens are. Right, here we go. Here is a function f. It's from 0 to 4. And it's asking you to find, using only this graph, oh God, look at that, L2, R2, and M2. Well, that won't take much work. If I wanted to do a 2 here, wouldn't you just have 2 strips? So wouldn't the first strip, the middle of the strip, be here? So you'd have 1 strip going this way and 1 strip going that way. And you would just decide which side, the left or the right, and that would get you these 2. Now, if you imagine the strip goes here, won't the midpoint use 1? So its strip would be here. And the second one would be at 3, so its strip would be here. And then it asks about under and over estimates, and you can check that yourself. Here's a function. Here's the viewing rectangle. And they're asking us to look at the graph and decide is it an over or an under estimate. If a function's increasing, won't a left be an underestimate and a right be an overestimate? Right? If a function is going uphill, won't the right-hand side consistently give you a big answer, an overestimate, and the left-hand side give you an under? So you should be able to hopefully figure out that guy. Here is a function. Oh, actually, that's kind of basically the one I did already, isn't it? Trapezium, Simpson, and do a midpoint. And the last one is, here's another function, trapezium, midpoint, and Simpson. So the last 2 questions are much more straightforward, right? Here's a function from 0 to pi upon 2, do it with 4 strips. Here's an ugly function from 0 to 4, do 8 strips. And that is the end of that guy. So we are, as I said, surprisingly ahead of the game, which is not a bad thing. So let me show you what 5-2 is. It's called an indefinite integral. That's its heading. Now, can you imagine a function y equals f of x? There's the start and the finish. And we want to find the exact area under the curve. We call that exact area, we write it down like this, the integral from a to b of f of x dx. Right, that's the notation that basically says, I want you to find the area under this curve from a to b, and the function is f of x. We do not want to find an estimate for this, we want to find the exact value. And the exact value can only be done in a limited number of ways. The first way is with that horrible thing I did at the start of today. Remember that 20-line algebra with the limit as n tends to infinity and sigmas and all sorts of stuff? That's one way to do it. Nobody in their right mind would ever do it that way. The second way to do it is that in certain circumstances, if you're really lucky, you can find the exact area under the curve by using geometry. In other words, I know how to find areas of rectangles, triangles, and circles, right? So as long as the shape I'm trying to find the area of is one of those shapes, I could get the exact answer just by using, you know, the area of this rectangle or that triangle added up. And that's what this section is going to deal with. And once this section is finished, we then do what is basically the most typical way of finding areas under curves. We are going to use a formula. Remember in calculus, we found formula, or rules, I guess I should call them. Product rule, quotient rule, power rule, chain rule. Remember all those different ways to find derivatives, but you do it totally algebraically, right? You don't do strips and limits or anything, right? Well, we are going to show you that you can find areas under curves in that same way by using rules. And we're essentially going to use a guy called antiderivative, which you did meet right at the end of Calc 1. So it'll be a kind of refresher for a start. Now let's go back to this guy. Here's a question. In fact, it's a version of question 1 from that section. And you're being asked to find the area from 0 to 4, the area from 0 to 10, from 10 to 14, and finally from 0 to 18. And I'm going to show you how you would be able to do it and get an exact answer. Let's start with the first one. The area from 0 to 4. Isn't it basically that shape? Right? Area under the curve. Now, do you notice that that shape can actually be done relatively easily by, if I can find another example of it, I'll do it over here. By splitting the shape into 2 pieces. I'm going to call this piece 1 and I'm going to call this piece 2. Now I'm going to add in the scales because I think it helps. Isn't this shape made up of a rectangle, which I'm calling 1, plus a triangle that's called 2? And the area of this rectangle is 4 times 2. And the area of a triangle is a half of its base, which is 4, times its height, which is also 4. And this guy is 8, and this guy, by coincidence, is also 8. So the answer to this question is 16. So do you see I managed to find the area under a curve without really making my life a misery?
I have a question.
Without, yes.
So you know the trapezoidal method like makes a line like that. Can we use that formula
Yes.
to find that part of the area?
You could, but I would suggest you don't, because isn't this a lot easier?
It does seem easier, yeah. But
Yeah.
it's the same
So
thing, right?
yeah,
Okay.
it's the same thing. It's a trapezium, and you could do it that way. You'd only be doing 1 strip, so it wouldn't really be much of a formula. Right, now suppose we move on to the next one, 0 to 10. Right, if I put in the extra guys, there's 10. Well, if you call this guy 10, can I split this shape into a rectangle, which I'll call 3, and a triangle, which I'll call 4. And if I add up all of those, won't that be the area from 0 to 10? Great. Now, it's shape 1 plus shape 2 plus shape 3 plus shape 4. Now, I've already found out what shape 1 and 2 are, right? We've already done them. That guy's 8 and that guy's 8. So let's focus on 3. It's 2 times 6. It's a rectangle. And what about 4? It's 4 times 6. So it's a half of base times height. And that's 8, add 8, add 12. And that's 12. So the final answer is 40. I like this method so much better than T8 and S8. I'm trying to sell this to you, but do you think that this is a much easier way to find areas under curves than trying to do all that tables and delta x's and 8 decimal places? And at the end, isn't that only an estimate? Or isn't this the exact answer? It is the real answer, the true final answer. So far, so good. Now, I'm going to show you something that's a little bit weird, but it's true. These shapes, I think I'm going to get another straight guy. Right, this fella here. When we talk about the area under a curve, right, we mean the area under the x-axis. Now, any area or any curve that's above the x-axis gives you a positive area. Any shape or curve that's below the x-axis gives you a negative area. Now, I know you were told you can't get negative areas. Technically speaking, these areas that we're calculating are not just physical areas, they're really net areas. And net areas means negatives are allowed. So, if you want to find 10 to 14, which is basically just this piece here. Would you agree that's just a triangle, right? From 10 to 14. And the answer is a half, its base, times its height. What would that be? -6 times 6. And half of that is 12, I believe. Let's check that. 4 times 6, yeah. But because it is below, underneath the x-axis, its integral, its net area, is -12. Can you imagine that these areas represent displacement? Couldn't you have a positive displacement, like 12 meters in front of me? Or -5, which means, oh, I went and walked backwards, I'm 5 meters behind me. Or 10 meters up or 12 meters down. Can't you have displacement positive and negative? So you can have positive and negative distance displacement. You are allowed positive and negative areas under curves. So just keep that in mind, that these guys are negative. And now we come to the last one. The area from 0 to 18. So from the start to the finish. So I broke it into that piece, numbers 1 and 2. I broke it into this piece, which is 3, this piece, which is 4, this piece here, which is 5, and that guy there is 18. And I think I would split this into a guy I'm going to call number 6 and a guy that's called number 7. So if you wanted to find all of this area, wouldn't you basically add up all the different pieces? So you would take numbers 1, 2, 3, 4. What about 5, 6, and 7? Am I going to add those or subtract those?
Subtract.
Because they are negatives. So when I wrote down -12, that's basically it. So I should have all my bits and pieces here. That guy was 8. We found that guy was 8. This guy was 12. Number 4 was 12. This guy was takeaway 12. This fella here is, what's that, 4 by 4, which is 16. And this little triangle is 4 by 2. And a half of 4 by 2 is, half of 4 by 2 is 4. And so what do we get? We get all of this and all of that. 40, take away 32. The final answer is 8. So the area under this curve from 0 to 18 is positive 8. Pause for a minute to let that sink in. A big chunk of pluses, a fairly big chunk of negatives. Net effect, 8. Is it possible for you to find an integral from a to b of some function and get the answer 0? Could the net area be 0?
Yes.
Yeah. Here's a very simple example of that happening. Can you imagine you did the sine function and you did it from 0 to 2 pi? Wouldn't this piece exactly cancel out that piece? Agreed? Could you get an area that's negative, a net area that is negative?
Yes.
Yeah, in fact, didn't we get one? That one. So it's okay to have negative answers when you're finished. It's okay to have 0 answers when you're finished. What we're doing here is we're finding areas under curves, but we're using geometry, right? We're using the fact that we know how to get rectangles and triangles, and so we can get exact values for all of these. And it's a bit like somebody giving you, I don't know, a cake, and you cut it into pieces, and then you add up all the pieces, add and subtract all the pieces. And that's how you would get your answer. So that is the first version of that question. Any questions before I move on to my next example? Okay, let's do that. Here we go. This guy. Now, what I have here, triangle, half a circle, little baby triangle, right? I'm going to put in all the x coordinates because for me it's hard to keep track of everybody if you don't. There we go. If you want to know the area under the curve from 0 to 6, aren't you basically just getting that one big triangle? So the answer is going to be half the base times the height, and I believe the answer is 36. And would you agree that's positive 36? Let's do the trickier one. 6 to 12 is this half circle. So I want to know the area under the curve from 6 to 18, I should say, that piece. Okay. Before I continue, what's the radius of this circle if you drew the whole thing?
6.
Agreed. How did you find it? You just knew by looking?
Yeah, it's just the midpoint to one of the edges.
Okay. And from there to there is what, 6 boxes?
Or you could do half.
6 units, I should say. Okay, so there to there is 12 when you half it. I don't really mind. Oh, there's another way. Couldn't you say from there to there is 6? I mean, as long as you know it's 6, it really depends on how your brain works. Some people just look at it and they know it's 6, but it's hard to put into words why they know it's 6, but they know it's 6. Now, this isn't a whole circle. It's a half of circle. So won't it be a half pi r squared? And it's going to be 1/2 pi times 6 squared, which I believe is 18 pi. And no, you don't turn that into a decimal. You don't go 18 times 3.14. You leave it as 18 pi. That's totally what we want. With one little change that I haven't put in yet.
The negative sign.
Because it's a net area that's below the x-axis, right? So it's negative 18 pi. Right, easy thing, almost missed it myself. Now, the last one is actually asking you to start at the beginning and finish at the end. So I'm going to use a clean one. We know this guy is 36, so I'm just going to write down what he is. And we know this guy here is 18 pi, or minus 18 pi if you prefer. So if you want the whole thing, don't you basically just take that guy, and one little baby one at the end? So it's going to be 36, take away 18 pi. This is above the x-axis, so it's add a half. The base is 3, and the height is 3. So it's going to be 36, take away 18 pi, plus, that's ugly, 9 halves. Okay, turn that into 60, 72 halves. Add that one, you get 81 halves. Okay, there's the best you can do, is 81 halves minus 18 pi. It might not look very nice, but that is, nonetheless, that is the answer to the exact area under this curve from 0 to 21. Do you feel comfortable about doing similar versions to these questions? Areas under curves, basically break it into bits depending on what you're being asked. Rectangles, triangles, and pieces of circles are the only things you're going to be asked to deal with. So as long as you can cope with them, you're fine. Still on this section, but a kind of different thing. Suppose I tell you that the integral from 1 to 3 of some function is 7, and that the integral from 3 to 9 of this function is 10. And I ask you to use this to tell me what the integral from 1 to 9 would be. And don't overthink it. It is actually very straightforward. If from 1 to 3 is 7, and from 3 to 9 is 10, you do. You just add them. Some of you were probably trying to do some really weird stuff. But essentially, the integral from 1 to 3 plus the integral from 3 to 9 added together is that guy. So the answer would be 17. Suppose I had a function from 1 to 10, I'll call it g of x, and it's negative 3, and I have 10 to 15, and it's 7, then what would 1 to 15 look like? Well, wouldn't you just add them? Intuitively, does that sound like it makes sense that that's kind of what it should do, right? You want to add things together. Well, shouldn't you just add what they're equal to together, right? If you want to combine them, I guess I should say. There's only 7 questions, so this is a very short one. I'm just trying to find some examples of what's happening. Now, here is a calculation. And there are no numbers involved here, but the integral from 1 to 10 of f of x, take away the integral from 7 to 10 of f of x. What would that be equal to? So you did 1 to 10, and then you cut out 7 to 10. What would you expect the start and finish, these are called the limits of integration, to be for this situation?
1 to 7.
Does that seem sensible? Because it's right. Intuitively, can you imagine you've got a whole bit, but then you cut off the end? So aren't you just left with the start? In this case, 1 to 7. How about this fella? What would be the limits of integration for this situation?
2 to 3.
Well, we all look at that and say, yep, that's what I would have said, because you're right if you did. Are we comfortable with that kind of process? So I'll do one kind of ugly version of that, and then we'll move on to another thing that's still in this section. Suppose you did the integral from 1 to 3 of f of x, and you add the integral from 3 to 10 of f of x, and then you take away the integral from 7 to 10 of f of x. What's the limits of integration for this combined calculation?
1 to 7.
Agreed? Right. If you want to see what it might look like, if you just focus on these two, when you combine these two, don't you get the integral from 1 to 10? And then you cut out the 7 to 10. And if you cut away 7 to 10, aren't you just left with the 1 to 7? Right. Does it make a little bit more sense now?
I'm not really following, but keep going.
Oh, okay. Better way of thinking of it. Right, we'll do visual. Suppose I had 1, 2, 3. And I told you that the integral from 1 to 3, that this piece in here was 10 units, right? That's what its area was. And then I told you from 3 to 7, which was this bit here, right? And I told you that this piece here was 20. Right, so I'm telling you the integral from 1 to 3 was 10. And I told you the integral from 3 to 7 was 20. What would you get, or how would you get what would happen if you added these together? Well, if you added these together, wouldn't you get 10 and 20 added together? Which is 30. But isn't 30 also the integral from 1 to 7?
Okay.
Right?
Yes.
And you can imagine having a thing like a cake, and then somebody cuts the bit at the end off and eats it and says, you have what's left. And wouldn't that be a bit like taking away from the big cake and this is all that I get to eat because that's what's left? Right? So that's like a subtraction version of that. If we are good, I'm going to move on to the last piece of what happens in this section.
I just have a quick question real quick.
Are we good?
One quick question. So if you have
Yes,
an integral from like 1 to 10, could you take away something like 4 to 6?
Yeah, but then you'd be left with two separate pieces.
Okay. That's what I thought. I was just curious what like the notation of that.
Yeah, so if you had this one and then you took away, say, 46, you wouldn't be left with a single integral. What you'd be left with is a 1 to 4 piece added to a 6 to 10 piece. It's a good question. But the answer wouldn't be a single integral. Wouldn't it be two separate integrals? Because you cut the chunk out of the middle, right?
Okay,
Which,
that's what I thought. I just wasn't sure how to write it. Thank you.
okay. Any other questions before we move on to the last piece that is in here? Are we good? I just thought of a joke. Did I insult the French last time?
You did not.
I don't think so.
Okay, so I need a minute just to gather my thoughts. The last bit isn't hard. It's not that reason. If a joke comes out of my head, sometimes I just have to tell you it's to get it out. And so I'm a great believer in not being politically correct. So I figure out, in my world at least, as long as I insult everybody, it kind of averages out. So I'm going to start by insulting the French. But over the next quarter, I hopefully will be able to insult everyone at least once, including Scottish people. And so it'll average out, right? So here goes. They're quite quick, and some people describe them as dad jokes. I don't, but some people have. Why do French people eat snails?
Why?
They don't like fast food.
Dad joke.
This is going to be tough. Okay. Did you like that one, Kyla? That was bad. Okay. Here's another one. What do French frogs eat?
French toads.
Don't know? No, that's a good one. French flies. Okay, why don't they have fireworks at Euro Disney? Well, every time they do it, the French army surrenders. What's the difference between toast and a Frenchman? You can make soldiers out of toast. Keep thinking of French ones. Did you hear that the French have a new tank? No. It's got 1 forward gear and 6 reverse. How many Frenchmen does it take to defend Paris?
How many?
Come on. Nobody knows. It's never happened yet. Okay, last joke. You've suffered enough. I like this joke. It's an old one. I've used it lots of times, but it came to my head. That was actually the first joke that came to my head. This aircraft is flying over the Atlantic, and they get to about halfway, and the pilot gets on the radio and he tells the three guys that are on the plane, the three passengers, one of them's an American and the other's a Scotsman and the third one's a Frenchman. And the pilot explains their situation, says, look, we're all going to die. We're going to crash into the sea. We've lost a lot of fuel. We're too heavy. We'll never make it to land. We've thrown out everything, including the parachutes. So all that's left is, I need somebody to volunteer. And so the three of them are looking at each other and nobody's moving. Finally, the Scottish guy says, oh God, he says, I've had enough. And he gets up and he goes to the door of the aircraft and he opens it. And he turns around to them and he says, for the glory of Scotland, and he jumps out. And the pilot gets on the radio and says, that's great, we lost a lot of weight there, but not enough, we need one more. So the American and the French guy are staring at each other and staring, and nobody's going to move. Finally, the American guy gets up and says, oh, I've had enough of this. And he goes over and he opens the aircraft door and he turns around and he says, for the glory of America. And he throws the Frenchman out. Okay, have I successfully insulted the French enough today? Okay, Ryan's the only one who appreciates my jokes. I am feeling very, okay, I've now got a thumbs up. No, this is just sympathy now, and I'm not taking it. Too late, so Guy, that's it, you lost 10%. You were just too slow. What on earth is that picture meant to mean, Sarah?
They were okay.
Oh, okay, okay. You got French ancestry, is that what it is?
No, I've heard a few of them.
Okay. Yeah, they are very old, aren't they? Okay. Well, imagine that you've been told that the integral from 1 to 3 of a function, this is the last part of 5.2. Imagine that you're told that this is 10, right? You're just given the information. Actually, I've just remembered this is not the last. There's another thing after this, but it's almost the last. And you're told from 1 to 3 of another function called g of x, and this is 12. What do you think, and again, don't overthink it, what do you think the area under the curve of the combined function would be?
22.
Yeah. Is it intuitive? Does it make sense that you probably just add the two pieces together? That would be the most sensible thing to do. And the good news is that's exactly what you do. As long as they have the same limits of integration, right? That makes sense that you can only do it with like things. For completeness sake, but I'm not going to ask you the answer to this because I'm sure you could predict it. You might be asked to do that. In which case, the net area could and is -2. I will ask you, for what? If not what, how would you get the answer to that? I'll take that.
Would you substitute the integral for f of x as 10 and g of x for 12?
And anything else?
Then
What about this 4 and this 2? Yeah.
Multiply them with 10 and 12.
Agreed. And hopefully I've done this right. So do you see that these things work, I think, very intuitively, don't they? That you can add and subtract and multiply integrals together, and they behave in much the same way that adding and subtracting normal variables behave, right? And so we will use these properties almost without thinking about them later on. It'll just be, oh yeah, well, kind of it's obvious that's what you were doing. You'll find that we'll use this in a later on situation. So keep that in mind. So I said it was the last, but I forgot one. So I'm now going to show you the one I forgot. It was dead easy to miss. Yeah. We are going to find the exact value of 2x plus 2, starting at x equals -4 and finishing at 3. And that's all you've been given. So the approach to how this is going to work. The first step is you draw the line 2x add 2. Okay, so at -4, right, the start, at -4, what do you get? -6, so I better make this line a lot longer. So -2, -4, -6, and then going up the way 2, 4, 6, 8, and at x equals 3, you would get 8, so there'd be a dot there, and at x equals -4, it would be here, right? And that would be my straight line. So you draw your straight line, hopefully square paper to make life easy. And I believe it's something like that. So far, so good. Now, we've already done this question. Don't we know how to get areas under curves as long as they're rectangles, triangles, and bits of circles? In this particular question, the pieces that we're going to deal with are this triangle that's below the x-axis and this bigger triangle which is above the x-axis, right? I guess I'll give that a name. I'll call this triangle A and I'll call this one here, right, B. So let's figure out how to get A. It's a triangle, so it's a half base times height, right? Now, the base is the distance from -1 to there, so that's 3. And the height is from here to here, which is 6. And that ends up being, I believe, 9. But because it's below, isn't it -9? So are we happy with this net area being -9? And then we'll do B. It's going to be a half. Its base is from here to here is 4 boxes. And its height is 8. And this guy ends up being, I believe, 16. So this fella up here is going to be basically made up of those two guys and a net answer of 7. Are we comfortable with what we did in that one question? In fact, unfortunately, there's only one homework question. It's not that one, but it's similar to that one. So you're not going to get an awful lot of practice. There's 2 questions that look like these guys. There's 1 question that looks like this, and the rest of them are these combination things that we did here. And that's that section over with. So I think we have enough time to, since you're doing so well, to get a chance at revising this fella, because this is going to make next week a little bit easier, I hope. I'm not going to go into why we need to find antiderivatives. Let's just get some practice at finding them, because it's a while since you've done the EndyCalc one. Antiderivative is basically working backwards, right? So can you imagine you had a function and it was called x cubed? If you differentiated it, wouldn't the answer be 3x squared? And when you go in that direction, right, from x cubed to 3x squared, this process is called differentiation. And you've done tons of that. Isn't antiderivative the process of going backwards? Which is starting with 3x squared and trying to imagine what function you would need to begin with, whose derivative would get you 3x squared, right? That's kind of a way to say in your brain. And there are ways, there are rules in which we can use to help us answer that question. So I'm going to show you some new notation that you may or may not have seen before. There's my function. Capital F of x is the notation that we will use to mean the antiderivative. So I need to find a function that when you differentiate it, gives you 2x to the 4. And the rule that we're going to use is called power rule, which is the same rule, the same name that you use to differentiation, but it uses the rule in a different way. Can anybody remember how you use it to find the antiderivative of 2x to the 5? Oops, almost said the answer there. 2x to the 4. What do you do to the power of x? Let's start with that then.
Add 1.
Add 1. Now, a little bit harder to remember because it just is. What do you do with the new power? Do you multiply by the new power or do you divide by that new power?
Divide.
Yeah. Now, if you differentiate that, shouldn't you get this? Right, that's what an antiderivative does. Let's do a quick check. Multiply by the power, reduce the power by 1. Ah, do you see the 5's cancel? You're left with 2, and that goes down to 4. Perfect match. So, in general, this is what it looks like if you want to see it written down maybe as a formula. If you want to find the antiderivative of ax to the n, like 2x to the 4, whatever it might be, the antiderivative is add 1 to the power and then divide by the new power. Okay, let's get some practice at finding some antiderivatives then of some powers. (10x cubed). Antiderivative. Add 1 to the power, divide by the new power. And style points, that's what I call this, is where you make things look pretty. It's up the ante. Not so nice. What would you get if you add 1 to this guy's power, the 10x? What power of x would you get?
2.
Yeah, so you get that. And then you divide by the new power, which if you simplify it down, which you probably will do in your head, is 5x squared. The number 5, or any constant, 5 is just an example, is a special case. What is the antiderivative of 5? What function would you need so that if you differentiated it, 5 would be the answer?
5x.
Are we good?
Don't we also have to like account for a possible constant at the end?
Yes. You're well ahead of me. Yes. And you tag in a plus C at the end to all of them. How about the antiderivative of e to the x?
Just e to the x?
Yeah, it's one of my favorite functions because its antiderivative is itself. What do you get if you differentiate e to the x? Oh, you get e to the x. See how it works? The old plus c is the arbitrary constant, as it's called. Oops. Sorry. I just gave the answer away. I put the thing in the wrong spot. What is the antiderivative of 1 over x? The antiderivative is log x. How can you check? If you differentiate that guy, don't you get 1 over x? If you differentiate this guy, don't you get e to the x? If you differentiate this, don't you get that? If you differentiate this, don't you get that? It's quite easy to check that you've done the correct antiderivative, because can't you just differentiate it and you should get the f of x that you're looking for? The plus c just disappears as zeros. These two catch people out a lot. Antiderivative of sine x. We'll do that one first. Antiderivative of sine x. Say
Would
again?
that be negative cosine x?
I want to see some thumbs up here. Is he right? Only one of you agree with him. At least one I can see. That's better. Yes, he is right. And antiderivative of cosine is sine. Now, why do people get that wrong? Because aren't your brains more used to differentiation? And so you mistakenly think sine gets you cosine. Well, that's true when you differentiate, but doesn't sine get you negative cosine when you find antiderivatives?
When we're entering these in WebAssign for the capital f of x, the antiderivative, do we need to put the plus c at the end for it to accept the answer?
Yes.
Okay.
Yeah, and I'm very careless about that. But yes, it will tell you you're wrong, even though you're 99% right. It needs a plus c in this type of question, if it says what's the antiderivative. Okay, I want to find the antiderivative of a square root. It's not a good idea to leave anything as a square root, because algebraically it's not very manipulatable. Can't even say that word tonight. Manipulate it well. So if you ever have to find antiderivative of square roots and cube roots, turn them into a fractional power. Now, according to the power rule, don't you add 1 to the power and divide by the new power? Agreed? So the power rule works even when the power isn't a whole number. Right? It works even when the power is a fraction. Now, if you add 1 to that, you get 3/2. Isn't dividing by 3/2 the same thing as multiplying by 2/3? So dividing by 3/2 is the same as multiplying by 2/3. That's where that guy comes from. And now we have style points. If the original question, which it is in this case, is square roots, you are expected to give your answer and return it back to square roots. Now, it's probably been a long time since you had to deal with fractional powers, but isn't 3/2? The 2 means it's a square root. The cube means it's a cube. So the square root of x cubed is what that would be. Here's a different puzzle. I want to find the antiderivative of that guy. Before I try and find the antiderivative, I need to write this guy as a power of x. How would 10 over x squared be written as a power of x?
10 times x to the negative 2.
Agreed. Have you all, does it come back to you that, you know, powers on the bottom are really negative powers, right? So x squared is the same thing as x to the negative 2. Now, once you've got that, the power rule is very, very versatile. You can use it even when the powers are negative, with one exception. Add 1 to the power. And nope, it's not -3. Add 1 to -2 and you get -1, right? You're getting up the temperature scale. Divide by the new power. But style points comes into play now. Although that may be correct, well, it's like 90% correct, it's not the way we'd want you to write it. Wasn't the original question written down as a fraction? So shouldn't this be returned to a fraction? We just don't write the 1. Is it coming back to us, antiderivatives, all the different kind of nuances, all the different things that you would expect to do? I got time for a few more. Where shall I go this time? This is a good one. This one will test you. What's the antiderivative of secant squared x? Somewhere in Calc 1 you differentiated a trig function and the answer was secant squared. That's the guy we want.
10x.
Nailed it. Yeah, well done. You're smiling. Did that come back to you the minute you saw it? You said, oh, yeah, that's the one. I forgot it. Right. We're all getting rusty. That happens. How about, oops, this one? I think this one's even harder. There is a function out there whose derivative is 1 over the square root of 1 minus x squared. It's a function that you probably only met fleetingly, right, for a couple of questions, and then, you know, you went and did other stuff. But it's still one of the functions that has an antiderivative that we need to know. Okay, I'll give you a clue. It's an inverse trig function. It's an inverse trig function.
Inverse sine?
You nailed it. Inverse sine. A little hesitant because you weren't 100% sure, but you nailed it. Well done. Do you know what the inverse cosine one comes from? Comes from this guy.
It's the negative of it.
You nailed it again. Okay, for our last question of tonight, I am going to write down the ugliest looking function in the world and it's made up of 6 different pieces, and your job is to find its antiderivative. All you basically do is find 6 antiderivatives, but I'm just writing it as one big question. Right, so here goes. You have 2 minutes. Find the antiderivative of that guy. No pressure, you got 50 seconds. And all of them except one, we've done something similar today. Last few seconds. Okay, I'm not going to pick on one person because that wouldn't be fair, especially at this time of the evening. But I will take volunteers for one piece at a time. That way we can have as many people contribute as possible. So if you want to, you probably should volunteer for the easy one first, right? So any volunteers for the antiderivative of 5? Just shout it out.
5x.
Yay, okay, you're safe, unless you want to contribute more. What about 4 square root of a half, which you have to call that, right? And that, well, I won't do it anymore. What's the answer to that one? Anybody got it?
8/3 square root of x to the third.
Correct. Hopefully you got that, guys. I'll pause with that one. I'll make that the last one. Right, here's a nice easy one for the next volunteer. 2x cubed. What'd you get?
1/2 x to the 4th.
I agree. The next one is a nice easy one, I hope. 3 cosine x's, antiderivative. Oh, I even told you it was plus. 3 cosine x.
3 sine x.
Correct. Negative e to the x. If you get this one wrong, you might as well just go home. Right, negative e to the x. Okay, I'm not insulting you. Yeah, obviously, right. Okay. Any volunteers for that one? Because I am going to do this one slowly, just to show you what it is.
Is it negative?
Any
Is
volunteers?
it negative
Say again?
16 square root x?
Let's find out. If you turn it into a fractional power, isn't it negative a half? Now, add 1 to the power and divide by that new power, and then convert it, and guess who nailed it? You did. Owen. Keep forgetting that guy, plus C. When you're doing your homework, eventually you'll get to do antiderivatives. When you're doing questions about finding antiderivatives as well, here, if it says it's wrong, well, you just do a quick check, because it could simply be plus C, right? Rather than you spending 20 minutes doing another really, doing something else, just go for the obvious. Did I put the plus C in? And then, work on it from there.